Hello everyone. Welcome to section 4.5 of chapter 4, and we're continuing talking about compounds and their bonds. And in this section we're going to talk about covalent compounds and how we name those and then how we draw those from their names. So covalent compounds form when you have atoms that are going to share electrons to complete their octets. And so typically what that means is that you're going to be looking at these groups 4, 5, and 6 on the periodic table here. These are nonmetals and they're going to be combining, and so we're going to see that anything in these groups is going, as long as it's not a metalloid, is going to follow this particular rule set. So a hydrogen molecule forms as atoms move closer to the nucleus, and so basically what has to happen is that they have to get close enough and they have to be in the correct orientation to where these electrons can be shared. And since it's so small and it only has one electron, it only has to have 2 electrons in order to be stable. And so it will share one of its electrons, and it happily does that with itself and just about any other element that can form covalent bonds and share. And so we see this a lot with hydrogen. That's why you see it on both sides of the periodic table often. So in a fluorine F2 molecule, each atom will share one electron to obtain the octet. So if you look at fluorine, fluorine has one of these valence electrons that's available for sharing, and so since that is the case, it can actually share with each other and form this F2, and you see that with these noble gases, the halogens in column 7A, that they will often do this and form a gas with 2 of those. To draw electron-dot formula for any of these covalent compounds, what we do is we start with the symbols for each one of them separately. The carbon, as you see, has 4 sides. You put those dots on 4 sides, and then if it's going to hook up with a hydrogen here, hydrogen only has 1. And so what happens is that since you have 4 individual electrons available, you can use 4 of these hydrogens to share each one of those and make 4 pairs. And so by doing this, you complete the octet of the carbon, and then you complete the needs of the hydrogen as well, because remember, hydrogen only needs 2. You can share more than 1 pair of electrons, and if you share 2 pairs of electrons, then that is called a double bond. And if you share 3 pairs of electrons, that's called a triple bond. And this happens when you don't have enough electrons to complete the octet. That's what you do. You revert to these double and triple bonds. So when we draw electron-dot formulas, first we must determine what the arrangement is. And if you're in my section, we've also talked about the NASB method. This is similar to that. It's just a little less mathematical and detailed, and so you can review this method on this video, and you can also review the NASB method and see which one you prefer. It's just, they'll both get you to the same place. So you determine the arrangement of the atoms. You determine the total number of valence electrons. That's your N number, if you recall, from NASB. You attach each bonded atom to the central atom with a pair of electrons, and then you place the remaining electrons using single or multiple bonds depending on octets or how many that you need. For example, hydrogen only needs 2 and boron only needs 6. So step 1, determining, and we're going to do this for carbon dioxide, CO2. Carbon goes in the middle, and you have oxygens on either side. you will determine the total number of valence electrons, and the way you do that is you have 6 valence electrons in your oxygen, and you have 2 of those, so 2 times 6 is 12, and you have 4 valence electrons in your carbon, and so that gives you a total of 16. So then you attach each pair to the central atom. So you have carbon in the middle, and then you attach or share one pair with each of your oxygens. Then what you do is you take your number, and remember it was 16, right? We're going to place the remaining electrons either using single or double bonds. So we're going to have, that's 4, so we have 12 left. All right, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Or CO. Now, there's a problem, right? Because carbon does not have 8, it only has 4. And so what you have to do is you have to bring this shared pair here from each of these over so that you can share those with the carbon, and then that gives you 8 around the carbon and 2, 4, 6, 8 around each oxygen. In nitrogen, each nitrogen atom shares 3 electrons to gain an octet. The multiple bond is formed by sharing the 3 pairs. So when you put nitrogen, you have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You have 3 on each nitrogen that are available because they're single and available to share. And so what we do here is we just, for ease of use, we move the shared pair over out of the way to the far left and far right hand side, and then we take each one of those unshared electrons and pair them up to nitrogen. And indeed, this is what happens with nitrogen gas. You have a triple bonded molecule. When you name covalent compounds, you have the first nonmetal in the formula. You name it by its element name. The second nonmetal is sort of like we did with those ionic compounds. You use the first syllable followed by the "ide." If you have a subscript in the formula, then you put use a prefix this time in order to tell someone how many of each of those metals, those nonmetals there are in the formula. When the vowels O or OA are together, then the first of those 2 vowels is omitted. I'll show you what that means when we're naming. So you name the nonmetal, the first nonmetal, by its just regular name. You name the second element in there by using the first syllable of its name followed by the IDE, like we did with ionics, and then you add the prefix to indicate the number of atoms that's in the subscript. And so these are what we use for those prefixes. Mono is 1, di, tri, tetra, penta, hexa, hepta is 7, octa 8, nona 9, and deca 10. And so that's as far as we go really in this class. So name the covalent compound NCl3. Now in these slides you're going to see a lot of detail on these, and so it's going to take you slowly, step by step. Okay. The first nonmetal's name is nitrogen, so we're going to call it nitrogen. Then the second element was chlorine, so it becomes chloride. And then the last step is you look and see how many of each one of these do you have. You have 1 nitrogen. You don't have to put the mono on here if it's the first nonmetal. okay? But the chloride we do, and so what we do is we add the prefix 4,3, which is tri. So this will become nitrogen trichloride. And there we are, nitrogen trichloride. These are just some common covalent compounds that you may encounter. Dinitrogen oxide. Notice that if you have more than one on the first nonmetal, you do use that prefix. Sulfur trioxide, sulfur hexafluoride, okay, carbon dioxide, and so we're going to continue to do a few of these. All right, so which of these names is correct? And again, the detail for these is going to follow, so I'm just going to work these on this particular page. All right, so we have the first nonmetal is silicon, right? So we know it's going to be silicon. Oops. All right, and then the last name is going to be chloride, and I usually just do these and leave myself a little bit of room for the prefixes. All right, and so how many chlorines do I have? I have 4, and if you look back, the prefix for that is tetra. So this would be silicon tetrachloride, which would be this one. P2O5. All right, so this is phosphorus and oxygen, which becomes, I better leave myself some room. Oxide. Okay, so then I just look over here. How many phosphorus do I have? I have 2. So if you remember, that is what? Di, and then that would be a lowercase now. Diphosphorus. And then 5 oxygens, and so that's going to be what? Pentaoxide. But since I have an A and an O together, remember that I'm going to have to change that. So it'll be diphosphorus pentoxide, because I dropped the first vowel. Okay, and so the first vowel in this case would have been the A. So diphosphorus pentoxide. All right, this last one, we have chlorine. Remember, it's going to be chlorine this time because it's the first one. And then oxide. And so we have 2 of these. So we have dichlorine. And then we have 7 oxygens. So it's going to be what? I'm going to take that out or take the A out. One of the 2, right? Hepta. Okay, well the A is first, so we take that one out. So that becomes heptoxide. And we just do that because it's hard to say heptaoxide. So it's dichlorine heptoxide, and so that would be number 1. Okay? All right, so here's some for you to practice on. Name these, then come back and let's see how you did. All right, let's look at this first one. You have carbon, and you have oxide. Now, how many oxides do we have? We only have 1 this time, right? So we're going to say carbon. We would say mono, but that would have 2 O's together. So this becomes carbon monoxide. You've probably heard of this one. All right, this one is nitrogen. What? Dioxide. Last one is phosphorus. Trifluoride. And the last one is carbon tetrachloride. Very good. And this will take you step by step. if you're not with me yet in speed, it takes you like each step, adding the "-ide", then deciding, and then putting them together. Okay? Writing formulas for covalent bonds. First, you're going to write the symbol in the order, and then you're going to write any of the prefixes as subscripts. So in diboron trioxide tells us that we have how many borons? 2, because di is 2, and oxide, we have trioxide, that's 3. That's it. That's how easy this is. A lot of students really like the covalent compounds. All right, so let's write these formulas. You can put me on pause and go ahead and try this on your own and then come back. All right, so phosphorus pentachloride. So the symbol for phosphorus is P, and then we're going to have some chlorides. All right, and we have how many? 5 chlorides, so that's PCl5 because we only have 1 phosphorus. Dinitrogen trioxide. Okay, so we have N. How many? 2, because di is 2, and oxide we have 3. Very good. And then sulfur hexafluoride, and hex is what? 6. And here's all your detailed stuff if you need to know the details. Okay? So when we've looked at naming over some of these sections, the ionic compounds and the covalent compounds. And remember, the way you tell the difference, because you got to know the difference in order to name them correctly, since we name them. The ionic compounds will have a metal and a non-metal, and that metal will be first. So if you see a metal, that's an ionic compound. If you see 2 non-metals, and if you remember how to tell that, okay, the ionic metal is on the far left of the periodic table. It's in groups 1A, 2A usually, can be in 3A, and then across that jagged line where the metalloids are on the right will be your nonmetals. So if you only have things from the right side of the periodic table, it's a pretty good bet that it's covalent. All right, and when you name ionics, you either the only polyatomic positive ion is going to be ammonium, and so it'll either be the metal name or ammonium if it's NH4. They will only form positive ions, okay? And you use the name of that element as the first name. Then if it forms more than 1 positive ion, you have to use those Roman numerals, okay? In nonmetals, you have a single negative ion or a polyatomic ion. If you have a single negative ion, you just use the name, first syllable of the name, and use IDE at the end. If it's polyatomic, use the name of the polyatomic ion. In covalence, though, you use the first nonmetal, and it's just its name, but you do have to use what? Subscripts, or if you're naming, you have to use what? The prefix that corresponds with that subscript, like di, tri, tetra, etc. The second nonmetal of that formula, you'll use, like you did with the ionics, the first syllable followed by IDE. So a compound is ionic if the first element is a metal or the ammonium ion. Okay, so when you see the formula, you know in this formula that K is the metal because it's written first. Now, you also look over and see that it's in group 1A or 2A, and so you know for sure. The covalent, it's going to have a non-metal written first, and so here is your nitrogen, and so that would tell you that you're going to have to use the prefixes. Okay, all right, so since we need to know whether it's ionic or covalent before we can name it correctly, let's see if we can figure out if these are ionic or covalent. So stop this. You can use your periodic table and make your decisions. Remember, you only really have to look at the first element in the formula to decide if it's ionic or covalent. If it's ionic, it will have a metal as the first element. If it's covalent, it will have a nonmetal as the first element. Alright, so sulfur trioxide is what I would call that, because sulfur is what? A nonmetal, and so therefore this must be covalent. Barium is a metal, so this one must be ionic. Ammonium, we know that one has to be what? Ionic. Copper is a metal, so it is ionic. And nitrogen is a nonmetal, so it must be covalent. Alright, see, that's pretty easy. As long as you can look at your periodic table, you can figure those out without even really knowing a lot of detail about these elements. And so you should be able to also name those, right? So sulfur trioxide, because it's covalent. Barium chloride, you don't have to put the di on there this time because it is ionic, so it's going to be barium chloride. Ammonium, what? Phosphite. Copper 2 carbonate. Did you remember the Roman numeral? And then finally dinitrogen tetroxide, because it's covalent. So sulfur trioxide, barium chloride, ammonium phosphate. Oops, sorry. I should have done the math on it, shouldn't I? Copper 1 carbonate, because this is a 2 minus, and you have 2 of these. So they must be a +1. I didn't go through my steps, did I? And so copper 1 carbonate, and then dinitrogen tetroxide. And that's the end of section 4.5. Come back to 4.6 and we'll further our study of compounds and their bonds.